Welcome to the 24th lecture in the course of Industrial Engineering and Operations Research. I will continue my discussion on Industry 4.0 and then tell something about Industry 5.0 also, which is yet to come, or some people say that it already started. So, we have been discussing about Industry 4.0, which is characterized by many new technologies, more automation, robots and cyber physical systems, etc. This discussion we did in the previous lecture. Now, we were also telling that modeling and simulation is very important part of Industry 4.0. Many times manufacturing processes can be simulated, and for that purpose we use techniques like finite element method, which are physics based models, and then we also do data based modeling also using the soft computing things, neural network, etc. But we can also follow the hybrid computational approach also. Say for example, FEM is very robust method. It is based on the physics of the process. It will give you solution, but it takes lot of time to generate a solution. So, therefore, what we can do, that we can generate lot of data by FEM and then we can train a neural network model, and that trained neural network model can give me prediction in a fraction of seconds. So, it can be considered as a guess value and which can be further used to input the FEM model, and FEM can fine tune the results. So, this type of hybrid computational technique can also be adopted, and I am just giving one example of finite element simulation of friction stir welding process. Now, in the FSW process, we have modeled using deform 3D. Deform 3D has capability to solve that coupled temperature displacement process. We can obtain stress, strain, strain rate, temperature, material flow and velocity of each point can also be visualized. So, we can get details. Thermal, mechanical and metallurgical responses of parts during exposure to heat can also be predicted. Thermal distortions, quench cracking and residual stresses can be predicted. So, we are seeing that some picture here, that there is a workpiece, base plate is there, then in friction stir welding some tool is coming and that tool is processing, and we have seen the temperature distribution contours during FE simulation in two conditions. One is the lubricated condition, other is the unlubricated condition. However, finite element simulations of FSW is computationally very expensive. So, just to give the idea that how much time it takes to generate solution for one particular set of parameters, we want to get the result, that what is the force, what is the torque. So, it is written that the modeling of FSW process is complex due to numerous variable parameters applicable during the process. Now, if we see some papers in the literature, that Meshless has used arbitrarily Lagrange-Eulerian approach, and it took that he simulated 5.44 second plunging using Forge 3 software in supercomputing facility, but it took 42 days to complete the whole analysis. Similarly, Wang in 2007 used the Lagrangian approach of finite element analysis. He did 1.5 second simulation time using 3.5 gigahertz Intel Pentium 4. That means actually in the physical space only 1.5 second was there, but for getting the simulation in a computer it took 14 days and 12 hours. Then Ashidi et al., they used arbitrary Lagrangian, Eulerian and Eulerian approaches, and it took 6.6 second simulation in Forge 3 software package, and it by arbitrary Lagrangian approach it took 12 days just for simulating 6.6 second thing. That means in the shop floor only 6.6 second machine was run, but here it took in the simulation 12 days 20 hours, and then in the Eilerian approach it takes 6 days 14 hours. Then Malik, he did coupled Eilerian Lagrangian approach, and he simulated 15 seconds of the process using abacus explicit, and it took 9.5 hours. So simulation time has been reducing with improvement in computational facility available. Now here in the deformed 3D, what we did, we did plunging for 6.33 seconds, dwelling 5 seconds, traverse 3.37 seconds, and total time was 48.33 seconds. This was the physical experiment, but when we use Lagrangian conjugate gradient iterative solver using Newton-Raphson iteration, then you see that total time it took 18 hours, and if we use Lagrangian sparse solver direct iteration, it took 14 hours. So you see that even then it is taking huge amount of time. So there is a requirement of study on reducing simulation time for practical utilization of FSW FE simulation. So there is a scope to refine that. Because of that, this one people have been trying to do various type of other techniques also instead of FEM, where you have to generate mesh again and again. After deformation, mesh gets distorted. You see that lot of triangles are there. Now they will get distorted. So people use meshless method also. So meshless methods became popular since 2000, but still not much progress has been achieved in this. There are still issues of computational time, etc. So meshless methods are group of numerical methods for solving partial differential equations on regular or irregular distribution of points. Mesh generation, costly mesh generation and remeshing is not required, that is advantage. Some methods are based on weak form of differential equation, while just others are used on collocation points. These are various techniques, but there are many type of meshless methods. Like one is reproducing kernel particle method, and another one is corrected smooth particle hydrodynamics method. Other is element free Galerkin method, in which one rolling process also has been simulated. Many such type of things are there. Then radial basis function collocation method is there, where we satisfy the differential equation at certain collocation points. In this we try to solve that an axisymmetric forging problem using this method, and we put the boundary conditions and governing equations which has to be satisfied at certain point. So we make a neural network type of, this is architecture, and we have I am not giving the full details of this, but I am showing the results that when we simulated, we made many grid points, but there is no mesh, and we are upsetting one cylinder. There is a fixed die, there is a movable die, and it is upsetting, and then finally we obtain the contours of strain rate, and here also we obtain the contours of the strain. But then we obtain the contours of hydrostatic pressure, then we obtain the contours of normal stress at 20% reduction. But this process also took a lot of time. So although we published one paper, but this work could not be progressed much because of lot of difficulties during the process. Then nowadays one technique is becoming very popular, that is called molecular dynamics simulation, MDS. So many people have done. We are not going into complete detail of that, but here we do atom by atom or molecule by molecule. We solve the equations, we apply the classical laws of Newton, and then we make simulations. Any process can be simulated. We need not know much about the physics of the process, and here I am showing some case study of cutting behavior of silicon, and it is being done, and MD performed using large scale atomic molecular massively parallel simulator, that means ramps. Okay. This is available, anybody can use that, LAMMPS. But what happens that here again the problem comes that there is a lot of computational time. So, these are some molecular dynamic simulation results which has been obtained, which has been reported in the literature. And then another approach is that using the crystal plasticity simulation instead of molecular dynamic simulation, where you go atom by atom. In crystal plasticity simulation of micro machining of single crystal material, this paper has been published in 2006. Here what we do that we apply the concepts about the crystal planes etc. See, we did micro scratching of single crystal copper which was having FCC structure. So, only thing is that you should have corresponding material large from the material science, whereas in molecular dynamic simulation any process you can model without knowing the physics of the process, because you are doing atom by atom. But here what happens that you have to get the rule. For FCC material behavior will be different, for BCC it will be different, those type of issues are there, but there are some results about that. And we are showing some results, comparison of results with experiments etc. So, principal force matches well with the experimental result. Principal force for the 45-degree direction was 40% higher than that for 0-degree direction, and which shows the anisotropy of the material. Crystal plasticity modeling is very important in if you have anisotropy in the material, then that can be properly modeled. Thrust force predictions were poor and they were not dependent on cutting direction. So, these are the some results, and which I am showing these pictures you can see. So, this is so if we just compare that molecular dynamics and crystal plasticity FEM, what are the advantages of molecular dynamics? It is useful when underlying deformation mechanism is not well understood. It gives fundamentally insight of the deformation processes. No prior knowledge of system evolution is required, but disadvantage is that there is increased complexity of the potential and computational cost for multi-component system. Time scale and domain size are very limited, that means actual physical process can be only in nanosecond. Even that you model, it will take lot of time, and domain size also you cannot, if you take a very small domain, even then there will be billions and trillions of atom. So, naturally you cannot take big domain. So, people are just trying to solve in a very limited domain, 100 Newton meters etc. If you want that I should simulate 1 meter area, then naturally it will take very high time, and then unrealistic strain rate far from real world situation simulated. Till now a molecular dynamic simulation is being done not on a very practical problems, and CP-FEM is computationally more efficient. It has capability to model reasonable this one spatial and time domains. Various deformation modes can be modeled like slip twinning etc. Materials with different crystal structure can be modeled. Then deformation mode dependency on various parameters can be incorporated. Capability to investigate individual deformation mode is also there. These are the advantages. Compared to molecular dynamic simulation, it will take much less time, but disadvantage is that phenomenological material laws needed to be established for new material via initial experimental investigation. So, you have to get the material from experiments, and it involves identification of deformation modes and calibration of material model. So, these are the issues, still people are working on that, and that is why nowadays soft computing based models are becoming more popular. Now, let me tell that additive manufacturing thing also, which is again one disruptive technology. Disruptive technology means that it has disrupted or it has finished many other technologies. That is what the advantage of this, or it is a influence of this process. and it is part of Industry 4.0. 3D printing is also called additive manufacturing. In fact, additive manufacturing is the proper name. It produces three-dimensional physical objects through layer by layer formation based on a digital blueprint. That means you make a CAD file drawing and then it will slice that object and then it will do that. So, it has proven to be compatible with industrial manufacturing beyond prototyping. So, there are so many additive manufacturing processes, it is not just one. So, we can classify by different ways based on raw material. It can be solid based, it can be powder based, it can be liquid based. In the solid based, we have fused deposition modeling. Suppose there is a wire, it is in the form of a solid and it is melted, and then you can make the plastic type of component, polymer based components. Then laminated object manufacturing, where we have sheets and these sheets are stacked one on the top of the other like that. So, this is a solid based. Then it can be powder based one, that where we try to get powder and the powder is fused. It can be fused, it can be melted, it can be adhesively bounded. So, in that we have one process which itself is called 3D printing. In 3D printing, we put the powder and we put some adhesive material and they bind together. And then selective laser sintering, that where with the help of laser, selective portion is heated by the laser heat and then sintering takes place. Sintering is that means that powder particles they diffuse and they make a bond, and there may be only partial melting, but it is not complete melting. But in selective laser melting, you have complete melting, and that melting can be also achieved by electron beam melting, although electron beam melting will be very expensive, because for electron beam melting you require a vacuum. And liquid based processes are stereolithography, perhaps the first process of additive manufacturing. Here some liquid material is there, it consists of photosensitive resin, and then finally by with light it gets secured, and this is how it is done. Next is polyjet, which is also liquid based. Based on the layer formation, there can be classification. One is the extrusion based, just like material is extruded in fused deposition modeling. Then sheet lamination, where they are laminated. Then in beam deposition, this is lens process, powder bed fusion, binder jet printing, photopolymerization, which is done in stereolithography, and direct light technologies. So, we are just giving that some background about stereolithography. It was patented by Charles W. Hull in the year 1986, and it relies on the use of photopolymers and curable regions. The laser traces the cross section of the pattern of the product. A build platform is attached to support structure. Platform is lowered for coating. Substrate is again raised, where the blade wipes the resin and layer is left on the part. For ensuring proper settlement of the liquid, the build platform is lowered by a layer, and this is the schematic diagram. There is a laser and scanning mirror is there, and we are selectively curing it. So, this is stereolithography. Now, we have selective laser sintering process, where we put a powder. You see from this cylinder the powder is thrown away here, and then after that we keep sintering one after the other, and there is a laser source by scanning mirror etc. it comes. So, it was patented by Carl R. Deckard in the year 1989. High power laser beam fuses the powders at a molecular level in a particular area of the build material. So, this is selective laser sintering, and powder bed is heated nearly to the melting point of the material to allow proper sintering of the powders, and roller present on each side of the build platform provides the direction to the powders for each subsequent layer. The particles lying in the powder bed, controlled by a movable piston, is free to move in the z direction, that means vertical direction. The movement takes place according to the prescribed layer thickness. Selective laser melting implies similar principle, but there it is a melting. Then 3D printing is basically powdered material are deposited on the substrate and they are fused by a binder sprayed by the nozzle. There is no melting, but basically the binder or glue is basically fused, sprinkled, and then it joins. Powders are misted with water droplets by capillary action. The size, shape and lithology of the powder along with the interaction with the binder play a dominant role. The built part is subjected to firing for sintering to take place and strengthen the binding. So, after that, once it has been built, then it is subjected to firing for sintering to take and then it binds that. Then laminated object manufacturing, LOM, it was patented by Michael Fagin in the year 1988. We are seeing the schematic diagram. A continuous supply of raw material sheet from a feed roll gets bonded to the previous layer. So, you know there is a continuous supply and this is being cut. A heated roller is passed over the layers where a heat sensitive adhesive which is already applied to the surface of the sheet. Then once the layer is built, the built platform is lowered where the excess materials gets rolled by a second roller to allow fresh material come over the blade platform. So, this is how that it keeps doing this one. Then laser engineered net shaping lens is there. It uses an extremely powerful source of either laser or electron beam. The nozzle is mounted on a multi-axis arm that can move in a multiple direction. So, it is a type of, you can say, robot which works that. The melted metal powders are infused in a substrate to create a layer. For solidification to occur and create a layer, the substrate is moved underneath the laser beam. The uniqueness of this process lies in its ability to use multiple materials at the same time. So, it can make that using different materials. Now, if we just say that features of different AM processes, so material extrusion process is FDM, raw material can be polycarbonate, ABS and PLA, layer thickness is 100 to 250 micrometer and there is no requirement of laser. In sheet lamination, LOM PVC sheet, aluminum sheet can be made and then layer thickness is 80 to 200 micrometer. 200 micrometer means 0.2 mm and laser requirement is there. In binder jetting, we have got 3D printing in this polyvinyl alcohol, metal oxide powder, polymeric powder, they can be used and layer thickness is 100 to 400 micrometer, laser is not needed. Material jetting is an example is inkjet printing, acrylic powder and calcium carbonate can be used, layer thickness is 5 to 200, there is no requirement of laser. Powder bed fusion, two type of processes, SLS and SLM. Now, titanium alloys, ceramics powder, polyamide, they can be used in SLS and in SLM we can use stainless steel, titanium and aluminum and layer thicknesses are about 25 to total 150, but there is a requirement of laser. Then direct energy deposition, example is laser engineered net shaping. We can make functionally graded materials where the properties will keep changing in a continuous manner from space to space, place to place, and we can do stainless steel also, layer thickness is 200 to 500, there is a requirement of laser. Photopolymerization, example is SLA, we can make plastic, glass, ceramic, layer thickness is 50 to 100 and laser requirement is there. Then we have, so it is examples that appear various, there are some benefits and limitations. SLA process which was invented first, it can fabricate nano composites, biomedical industry uses it, hybrid polymer ceramics. Benefit is that good surface finish, fine resolution, thin layer thickness, but limitation is that limited range of materials are there, small product size and it is expensive. FDM has become very popular, you can purchase in say 5,000 and 10,000. So, it can fabricate prosthesis, polymer type of product, it was used in rapid prototyping, but it is high speed, low cost and sustainable material can be used, but limitation is that layer by layer appearance is known and it is not that precise and smooth. Temperature fluctuations is there, inability to get sharp edges. Then SLS is that you have lightweight structure, electronic components, defense hardware, and it can be used for, but it has poor surface finish. Similarly, lens has been used popularly for retrofitting, etc. It takes less manufacturing time, but it has less accuracy. 3D printing, it makes structural parts, it is fast fabrication, but it is fragile and it has porous thing and it is rough surface finish. LOM can be made, it is inexpensive, but it provides less dimensional stability. So you see that there are some pros and cons, and nowadays people are focusing on the sustainability of 3D printing process. So therefore now issues are that in additive manufacturing we have to see these things, that how it can be competitive with other manufacturing processes. Then we have to improve the speed, then mechanical properties have to be studied and they have to be characterized properly, they have to be improved. Cost is very high these days, that cost reduction has to be done. Availability of raw materials is often sometimes issue, and we have to see overall sustainability. Now Industry 5.0 is a proposed fifth industrial revolution that builds upon Industry 4.0, emphasizing human centricity and sustainability. So basically the human being is in the center. It aims to create a more sustainable and resilient industry by balancing technological advancements with the well-being of workers and the planet. So advantages are that it has got human-centric approach, it can be more personalized, it focuses on sustainability, it focuses on resilience, that means it builds systems that can adapt to disruptions like pandemic, COVID, etc. and supply chain shocks, and then enhanced innovation, better work conditions and social responsibility. It focuses more on social responsibility. So here is a quick comparison between Industry 4.0 and Industry 5.0. Industry 4.0 focuses more on automation, efficiency and productivity, whereas Industry 5.0 is human-centric, sustainable and resilient manufacturing. Role of humans in Industry 4.0 is not that much as it is in Industry 5.0. The machines and human beings collaborate with each other. So we make cobots, etc. Production type is smart mass production, but here it is smart mass customization. Then similarly we can say sustainability in Industry 4.0 limited focus, in Industry 5.0 strong emphasis is there, and innovation approach. Industry 4.0 is machine-led innovation, but here it is co-creation between humans and machines. Ethical considerations in Industry 4.0, not much discussion on the ethics, but here there is an emphasis on ethics, inclusion and social impact. End goal of Industry 4.0 was smart factories, but Industry 5.0 end goal is harmonious coexistence of technology, people and the planet. So this is what Industry 5.0, where you know that human beings will also play important role and humans and machines have to coexist together. This is the approach we are following. So that's all for today. Thank you very much for your attention.